Hi, my name is Rajendra Kumar. I am a PhD candidate in the joint degree program of IIT Kanpur and NUS Singapore. Today I will be talking about hardness of approximation of multi LCS over small alphabet. This is a joint work with Ame Bangale and Diptarka Chakravarti. Let's start with the introduction to multi LCS. We are given k strings s1 to sk of length at most n over alphabet sigma. The problem here is to compute the length of the longest sequence that appears in all strings as a subsequence. Let's see this through an example. Let's consider sigma as a set of 4 characters A, C, G, and T, and let's take n equal to 12. As you can see, S1 and S2 are two strings of length at most 12 over alphabet sigma. And S is the longest common subsequence of S1 and S2, and the length of S is 6. So given S1 and S2 as the input string, the problem of multi-LCS is to compute the length of the longest sequence, which is 6 in this case. Now we know what is multi-LCS. Let's see some of the known results on multi-LCS. It is known that when number of input strings are unrestricted, this problem is NP-complete. In our case, when k is allowed to take any arbitrary value, this problem is NP-complete. There is also a fine-grained hardness result known for this problem, which says that under strong exponential time hypothesis, for k strings, any algorithm for multi-LCS problem must take at least n to the k time. This result was given by About et al. In 2015. Let's see what strong exponential time hypothesis says. So the strong exponential time hypothesis says that for any constant epsilon greater than 0, there is no 2 to the power 1 minus epsilon n time algorithm that can solve satisfiability problem on n variables. So we know that the multi-LCS problem is NP hard, and whenever a problem is hard, we always look for approximate solutions. So now we move to approximation of multi-LCS. A gamma approximation of multi-LCS, where gamma is approximation factor less than or equal to 1, the decision version is defined as follows. Given S1 to Sk, k strings of length at most n over sigma and an integer L, the problem is to distinguish whether the input is a yes instance or no. The input is a yes instance when LCS has length at least L. The input is a no instance when LCS has length less than gamma times L. It is known that for any alphabet sigma, 1 by sigma approximation is easy. The idea here is to find the longest common subsequence with one character. Repeat this algorithm for all the characters in alphabet set sigma, and then output the length of the longest sequence among them. This gives us the 1 by sigma approximation of multi-LCS. Now let's look at some of the hardness result known for approximation of multi-LCS. So Jiang and Lee gave a reduction from max click to multi-LCS. This reduction almost preserves the approximation factor. Then Zuckerman shows that n to the power 1 minus epsilon approximation of max click is NP hard for any epsilon greater than 0. As you can see, combining these two results, we get that n to the power 1 minus epsilon approximation of multi-LCS is NP hard. But this reduction only shows the hardness of multi-LCS instances when alphabet size is at least n. So we ask the following question. What can we say for small sigma or small alphabet size? Is 1 by sigma approximation is the best possible we can achieve in polynomial time? As we have seen in the previous slides, this is the best which we can hope when sigma is order of n. Prior to this work, there is no other hardness result known for multi-LCS problem when alphabet size is small of n. In this work, we make the following contribution. We show that assuming the exponential time hypothesis, there is no polynomial time algorithm for gamma multi-LCS, where gamma is the approximation factor which is greater than equal to n to the power minus small of 1. And sigma is the alphabet size, which is equal to n to the power small of 1. Here, the assumption is exponential time hypothesis, which says that satisfiability problem on n variables cannot be solved in 2 to the small of n time. Now, before going into the detail of the reduction, we will define some graph theoretic problems which we're going to use in our reduction. Let's consider we are given a graph G on n vertices and an integer k less than equal to n. Gamma is the approximation factor, which is less than equal to 1. The problem of gamma max click is to distinguish whether the input is a yes instance or no. Input is a yes instance when there exists a click of size k. It is a no instance when there is no click of size at least gamma times k. Remember, complete subgraph of G is called as click. The problem of gamma densest k subgraph is to distinguish whether the input is a yes instance or no. The input is a yes instance when there exists a click of size k, and input is a no instance when all subgraph of size k have density at most gamma. Here, the density of the graph is equal to number of edges in graph divided by the number of edges in the corresponding complete graph. As you have seen, the gamma max click problem and gamma densest k subgraph problem differs only in the no case. Now we will talk about the reduction outline. So we are going to start from reduction from max click to multi LCS. This reduction implies that largest click size is equal to size of LCS. Then we will show the alphabet reduction step where we replace the character by a string of length m over a small alphabet. Then we show the completeness of the proof, which says click of size k implies LCS of size at least k times n. And then we go for soundness, which is large LCS implies there exists a large dense subgraph. In rest of the talk, we will talk about all these steps in detail. Let's start from reduction from max click to multi LCS. This result was given by Jian and Lee. Let's assume the vertices are ordered from V1 to Vn. For each vertex Vi, we create string xi and xi prime. The string xi has the vertex Vi in between, and before vertex Vi, all the vertices other than the vertex Vi appears in the order which is already decided. And after Vi, all the neighbors which have index greater than Vi appears. In string xi prime, vertex Vi appears in between, and before vertex Vi, all the neighbors of the vertex Vi with index less than Vi comes, and after vertex Vi, all the vertices except vertex Vi appears in the order. So we get that for all Vi's in common subsequence of x1 to xn and x1 prime to xn prime forms a click. And we also note that all the vertices in the click appears in all strings. So in total, we get that there exists a click of size L if and only if there exists common subsequence of length L. Now let's see this through an example. We are given a graph G of vertices V1 to V8. And in this example, we are going to construct a string x5 and x5 prime corresponding to vertex V5. As you can see, V5 has 5 neighbors, V1, V3, V4, V7, and V8. V1, V3, V4 are the neighbors which have index smaller than V5. V7 and V8 are the neighbors with index greater than V5. In x5, initially all the vertices appears other than the vertex V5 in the ordered manner. Then vertex V5 comes, and in the end, all the neighbors of V5 with index greater than V5 comes. In string x5 prime, initially all the neighbors of V5 with index smaller than V5 comes, then the vertex V5, and in the end, all the vertices except V5 are there. As you can see, LCS for this case is V1, V5, or V8. There are many other LCS, but all the longest sequences are of length 3. And you can also see that in this graph, click is also of size 3. And V1, V5, V8 also forms a click. So the reason for this is, if any vertex Vi appears in the LCS, in this example, let's take V5, then the vertices on the left hand side of it, which is V8 in this case, is also a neighbor of vertex V5, and that is because of string x5. And the vertex which is in the left hand side of V5, V1, that is also a neighbor of vertex V5 because of string x5 prime. So we get that there exists a clique of size L if and only if there exists common subsequence of length L. Now we move to alphabet reduction. In this case, we replace each vertex by a string of length m over small alphabet small sigma, where small sigma has size less than n. And then we replace all the vi's in string xi by si, and we get strings yi and yi prime. The completeness still holds because we are just replacing the characters, and all the mapping which were before the replacing the characters still holds. So the LCS increases by a factor of m. So we get that clique of size k implies LCS of size at least k times m. What about soundness? In soundness, we have some issues. First is SI may not map to SI. It is possible that SI may map to some other thing. There is also a possibility of partial mapping to SJ. So we'll analyze these two cases. So first, a natural idea of selecting the strings SI is select the string SI such that LCS of SI and SA is small. And one way of doing it is pick S1 to Sn uniformly at random. And with high probability, the LCS of these two strings will be, for any two different strings, is very small. It is less than equal to alpha times m. And the alphabet size is order of 1 by alpha square. And the length of the strings is 1 over alpha square times log n. This result was given by Kiwi et al. In 2005. Now we will break our result into two different parts. So in this proof, we try to show that if there is no polynomial time algorithm for beta by 4 densest K subgraph, then there is no polynomial time algorithm for 2 square root beta multi LCS, where alphabet size is order of beta to the power minus 4. And here beta is equal to k square by n square, where k is a parameter associated with densest K subgraph problem. And there is also a result by Manurangsi in 2017, which says that under exponential time hypothesis, for gamma equal to n to the minus small of 1 and k equal to n to the power 1 minus small of 1, there is no polynomial time algorithm for gamma densest K subgraph. So you can see combining our theorem and the result by Manurangsi gave us our desired result. Now we will show the proof of this theorem. So completeness directly follows that we know from the previous slides that large clique implies large LCS. To show proof of soundness, we show that if G is a no instance of beta by 4 densest K subgraph, then LCS has length less than 2 beta m. And a no instance of beta by 4 densest K subgraph means that all K size subgraph has density smaller than beta by 4. Also note that we are choosing strings Si to S1 to Sn such that any two different strings have LCS less than alpha times m, where alpha is approximately equal to beta square. Now let's talk about proof of soundness. For rest of the analysis, we assume that LCS has length greater than 2 beta mn, and we will show that there exists a dense subgraph. As you can see, this is the contrapositive statement of what we have stated in the previous slide. We know that the string yn is equal to S1 to Sn, and the reason is the vertex Vn has the highest index and there is no neighbor of vertex Vn which have index greater than n. Let L be the LCS of y1 to yn and y1 prime to yn prime. As L is also a subsequence of yn, the LCS L is of form z1 to zn, where for all I, zi is a subsequence of si. Now from LCS L, we remove the small zi blocks. We only keep the blocks which have length greater than beta times m, and we call this new string L prime. As you can see, when we go from string L to L prime, in terms of length, we lose at most beta times mn. Let V prime be the set of all the vertices Vi such that corresponding Zi is in string L prime. We also bound the size of set V prime. Here we use the assumption that L is greater than 2 beta mn, and when we generate the string L prime from string L, we lose the length at most beta mn, and we get that the size of set V prime is greater than beta times n. Let Cij be the set of all the blocks Zt in L prime such that the index t is between I and j. We use this notation to capture the number of blocks between index I and j. So when we take the ratio of the cardinality of set Cij divided by the difference j minus I, we get the density of the number of blocks in L prime between index I and j. Now we will talk about the sketch of the proof of soundness. In this case, first we show that in L prime, there exists the bunch of intervals in which the density of the number of blocks Zi is small. In this example, those indices are P1, Q1, P2, Q2, PL, QL. And in step 1, we show that for all j less than equal to L, the ratio of the cardinality of C of Pj, Qj divided by the difference Qj minus Pj is small. Let A be the set of all the blocks Zi which are in these intervals. And as LCS is large, we get that the size of set A is very small. So the most of the blocks Zi which are in string L prime are not in set A. So all the blocks which are not in set A, we show that the corresponding Vi has high degree. And when we see the subgraph containing these vertices, the subgraph has high density. And through these arguments, our proof follows. Till now, we have only seen the randomized result, and the randomization comes because of the construction of string Si. Now, to de-randomize our result, we use the construction of long-distance synchronization strings. And the idea of long-distance synchronization strings is to construct a string S such that if we take two non-overlapping intervals, then the LCS is very small. And as you can see, this gives as exactly the same guarantee as the random strings, but with slightly larger alphabets. With this, I want to conclude my talk. In this work, we have shown that under exponential time hypothesis, there is no polynomial time algorithm for n to the power minus small of 1 multi LCS when alphabet size is n to the small of 1. Over reduction can't give hardness for constant alphabet as the gamma tensors K subgraph problem for the corresponding parameter gamma and K is easy to solve. And the open problem here is to either give the hardness or an algorithm for constant factor approximation of multi LCS for small alphabets. Thank you for your attention.